Okay, this is the last section of Chapter 8. It's called Energy and Chemical Reactions. What we're going to talk about in this one is what it takes for a reaction to actually occur successfully, as well as the energy that's absorbed or given off in the process. So for a reaction to occur successfully, three things actually have to happen simultaneously. The atoms actually have to collide. They have to come together. Not only do they have to come together, they have to be lined up right. So if we're talking about a bond breaking and another bond forming, for instance, if we have water and we're trying to add another hydrogen to it, we can't add another hydrogen here. We have to add it here. So it has to hit it in just the right spot. So not only does it have to hit it, but it has to be lined up perfectly. And then finally, it has to have the energy in order to break bonds and form new bonds. And if that energy doesn't occur, then a reaction can't occur. And we're going to talk about that a little bit more. That energy that I was referring to is right here. It's the activation energy. This is the energy it takes. Here's the original, here's the reactants on the left side of the equation. Once they actually come together, they have to have enough energy when they bounce off of each other to break those bonds. And then this downward side is the forming of the new bonds. There's two types of energy in the reactions. There's exothermic and then there's endothermic, which I'm going to talk about in a minute. And all that is saying is if there's more energy at the beginning than at the end, or vice versa. And what that's referring to is the bonds themselves. If the bonds take a lot of energy to hold together, and yet the products don't, that's going to be exothermic. That means that the energy is released. Notice it's on the right side of the equation here. So exothermic, the energy is released. It gets hot. If you are actually in the lab and you notice that something is getting warmer, that means it's an exothermic reaction because it's giving off the heat. Endothermic is the opposite. Notice they still have this activation energy here. However, this one's much, much greater because the fact that the energy of the reactants themselves are so low. They have to overcome a lot to want to break because they're so stable. Instead of the energy being given off, it's actually absorbed. If we say that there's an arrow here and the products are on the right, the energy is on the left side because the energy is being absorbed. And once again, the energy of the reactants are lower than that of the products. So that means the ones of the reactants are actually more stable. If you were to actually feel this, it would be getting colder as it's reacting. Think enter, so the energy enters. Energy enters the reaction. Alright, so let's take a second to determine if these are exothermic or endothermic. In reality, all you had to do is look at what side the actual energy is on. For instance, here it is on the right-hand side. That's part of the products, which means that energy is giving off, which means it's exo. However, this time it's on the left, which is the reactants, which means that the energy is being added in order for it to happen, which means it's endo. And then finally, it's less specific, but it gets the point across that heat is given off. as a product, which means, once again, it's exo. The reaction rate is essentially how fast the reaction is going to occur. So how fast the reactants are used, how fast the products are made. There's a couple different things that can happen to make it speed up. For instance, typically, not always, but typically, if you increase the temperature, it's going to go faster. The reason for that is, if you remember at the very beginning, you need collisions and the right orientation and enough energy. Well, by adding heat, you're adding energy to it. So that increases the energy right there. You might not be able to affect the orientation of the collisions where they're hitting each other, but what you can affect is how many times. And so if you increase the collisions, you're increasing the likelihood. And also if you have more reactants there. If you have more reactants, once again, you're increasing the amount of times or the likelihood that they're going to bump into each other. And finally, you can do it with a catalyst. A catalyst is there at the beginning and it's there at the end. It doesn't actually get used up in the reaction. It just helps the reaction along. It kind of adds an extra step. It lowers, here's the original activation energy. It lowers the activation energy by that much. Essentially, you're adding an intermediate step. Like if you had to go from A to B, it's like you're going from A to A.5 to A.5 to B. You're adding an extra step in there, and it's going to be something that bonds to the reactant much easier, and it creates kind of a pathway, a tunnel to get to the product. So just as a review, things that can actually increase the reaction: the concentration, because you're increasing the likelihood of them bumping together, increasing the amount of times they bump together. The temperature, once again, you're increasing the quantity of bumps. And a catalyst, you're lowering that activation energy so it doesn't have as much of a hurdle to go over. Okay, let's take a minute to review. So, is the reaction rate going to increase, decrease, or have no effect? Well, increasing the temperature increases the amount of how fast they're moving, which is then going to increase how many times they bump together. This is going to increase the rate of reaction. Removing, so we're taking reactants out, that's actually going to end up decreasing it. Because remember, if we add stuff, it's going to make it go faster. So if we take away stuff, it's going to make it go slower. Adding a catalyst is going to be an increase, because you're lowering that activation energy. You're making it less of a hurdle to get over in order for it to work. Putting the flask on ice, that's going to lower the temperature. Notice A, we increase the temperature, while putting it on ice will lower the temperature, which means that will decrease. And increasing the concentration of one of the reactants. You're increasing the concentration, so you're increasing the likelihood of them bumping together. So that's going to increase. So let's do this little check. Raising the temperature. Well, in general, raising the temperature usually increases it, because you're increasing the amount of times that they're going to bump together. Adding oxygen. Okay, so we're adding oxygen right here. That means we're adding more of the reactants. That means it's going to increase, because once again, you're increasing the amount of times it's going to bump together. adding a catalyst. You're adding an intermediate. You're adding a part B to it, so that way it has a shorter hurdle to go over. And lowering the temperature. Well, if raising the temperature increases, then lowering the temperature must decrease. And that's because you're reducing the amount of times they're going to bump together. Alright, and that is the end of section 5.8. Do not forget to review. And good luck.